Okay. I tried to be short, and so this is somehow reflecting my personal experience with Steve Smale in the past 2 decades. I'm old already, not like before. But one question, I guess, Lenore was not here. We just want to ask, this is a common machine, modern AI illusion. So if you look at this picture closely, you see some rocks, but I guess all the people sit in the back of the classroom see this is a scholar reading a book. But what's the truth, or is that conscious? What your unconscious way to tell you what's the picture meaning? I don't know the answer. But anyway, in fact, I already participated several birthday conferences in the past 25 years. The first one is 2000 in the year 2000 in CityU. I guess some of you already there, maybe Tommy Poggio. And at that moment, I'm pretty young as a kid. And 10 years later, this is 2010, when Steve Smale came back to the CityU in Hong Kong second term. And then I'm already working in the Peking University as a junior faculty. And this is the 2021st. We cannot have the on-site birthday conference, but still Steve feels very happy with this online meeting organized by Xuan and Indica. And so now we are the 95th birthday, so I just want to say hopefully happy birthday. Hopefully we have some new one in the next years and so on, and more pictures will come. And I first met Steve Smale in year 1999. I graduated as a electrical engineering student from Harbin Institute of Technology. I didn't study mathematics in my undergraduate, but at that moment, very interesting link because I'm very interested with the chaos theory and Steve Smale working in CityU. That attracts me to apply to be his student there. And fortunately, I got admitted and joined CityU in the 1999. And at that moment, starting with the Master of Philosophy, that's a kind of thesis master degree in CityU at that moment. But the interesting thing is 2 years later, Steve returned to UC Berkeley. So I just followed him to visit UC Berkeley during 2001, 2002. And then I got a very precious chance to transfer to be a student, or readmitted as a student at UC Berkeley here in math department. Then I finished my PhD thesis here with Steve Smale, and also my committee include Peter Barley and Bin Yu, but Bin Yu later was absent from my thesis finishing, then replaced by Steve Evans. So that's the rough story. But during this period, I often visit Chicago because Steve Smale worked in Chicago part-time. Then Pasa Nyogi also become my mentor. So I know Misha there, so it's a long time ago. And in the thesis work, we start working on the dynamic serial learning. In other words, that's called online learning as the gradient descent, and so on. But after that, I went to the Stanford University working with the Gunnar Carson's group as topological data analysis, and particularly Hodge theory for preference learning. Just now, Grisida talked about the social choice. Actually, Hodge theory can give you a tool like a Fourier transformation for the preference data to shed light on how the social choice and possibility really arise. So that's my rough experience. But around the year 2009, both Steve and I went back to Asia because of the pandemic. For me, because of the financial tsunami just 1 year before that. And I joined Peking University in 2009. Then Steve Smale come back to CityU in Hong Kong in 2009. And then we are working in a parallel distance in Asia at that moment until 2016. Steve Smale retired again, finally returned to Berkeley. But I joined Hong Kong again to the slight different university called Hong Kong University of Science and Technology, which arguably has a better view than the CityU, perhaps. Okay, anyway, that's my path with Steve Smale after meeting him. And my motivation to study in those 2 decades actually comes from this Smale 18 problem. Michael already introduced that. But at that moment, when I just joined the CityU in 1999, Steve published this 18 problem in this mathematical intelligence, this paper. And all the other questions are pure mathematical questions, but only this one is not mathematical, but I'm from electrical engineering. So I feel this question attracts me the most, although I don't have answer. But this question actually motivates my pursuit in the next 2 decades following this. So when I was quite young, actually, I read, maybe this is the first serious attack thinking about the limits of artificial intelligence at that moment by Marvin Minsky, papered in 1969. They published this book, that's Tommy Poggio's colleague. And in this book, actually, he pointed out 2 facts. The very popular perceptron single-layer neural network at that moment cannot do XOR classification, which is very popular in computer science. But the second question is much less popular. This criticized perceptron or any parallel machine needs infinite global information to compute topological environments like connectivity. And in fact, the second question captures more attention from mathematical society, but the first one is from computer science. So they also argue that the locality or sparsity is from intrinsic constraint in any intelligent machine. So you already see Tommy Poggio's compositional sparsity enoration just now. And I won't talk about this too much, but the questions, in my experience, this 1986 paper by Hinton, they show using the stochastic gradient descent, one can learn multi-layer perceptron, the representations published in this 1986 paper. But the people at that moment mostly noticed that with this algorithm, MLP can correctly solve the XOR. But the very few people really look at the topology computation. So actually, Minsky's claim still exists there. One cannot compute the connectivity for arbitrary shape using the parallel machine. So this kind of answer will be disclosed until Bloom, Shub, and Smale developed the notion of real machine, at least mathematically rigorous way to solve this one. And the motivation for Steve Smale and Bloom and Mike Shub to develop the notion of real machine partially come from this Roger Penrose's 1989 critics. He also think about because the BP algorithm, and there is a second rise of AI at that moment, and Roger wrote this book to criticize. Actually, he tried to think about the limits of AI at that moment. So this Emperor's New Mind argued that maybe Turing machine as AI's foundation is insufficient. At least he raised is Mandelbrot set computable? This cannot be answered within the Turing machine concept. So that's how the BSS model developed. So they start from a paper with Lenore, Mike, and Steve in the 1989 about the real computation. And in this abstract model, you admit the inputs and operations based on the real numbers or even complex number with infinite precision. But the most important concept in this kind of real machine, which is different to the classical Turing machine, lies in the concept of condition number. Condition number means that give you a way to measure the closeness of an input problem instance to all the L-post instance set. So this distance, the inverse of this distance, will be called the condition number. So this claim, this is written by Richard Karp in the preface that points out the crucial difference between the real machine and the classical Turing machine. And maybe that's not easy to understand, but let's take one simple example. Marvin Minsky's critics actually can be precisely answered under this real machine scheme. So not all the manifolds, arbitrary shape, can be learned, the topology can be learned using finite sample. Only a subset of them they call the stable manifold. Stable manifold means given any manifold like this curve, that cannot change topology under small enough perturbation, arbitrary small perturbation. So this kind of manifold, you can think that's the stable manifold. This kind of perturbation usually measured by the distance to the L-post set. So in other words, measured by the condition number. So if the stable manifold has a certain distance from the L-post one, when the topology will change under arbitrary small perturbation, then this kind of manifold, stable manifold, you can learn using a finite number samples. So this is the kind of a paper written by Pasanioghi, Steve Smale, and Shimon Weinberger in Chicago in 2008. So that precisely answers the kind of thing. And the most important notion in this thing is you need some stability for the shape, for the input to be learned or to be reconstruct from finite information, the sample. That's the precise mathematical theorem. But nowadays, if we come to AI, which is rapidly developing, you find this kind of stability, in fact, lost. I would like to say use this slide to say hallucination is ubiquitous in AI nowadays. The first line is very famous in computer vision, image recognition. You can see this is a black hole. For the first time, human take a picture of this black hole. But if you add this very small pattern, that results in this picture. But for any human eyes, you can immediately think there's no difference between these two. That must be a black hole. But for computer, if you trained a neural network from ImageNet, with high confidence, you can say that could be donut or could be, in fact, anything else, depending on the pattern you add. A human imperceivable pattern can change the category of a computer neural network output arbitrarily. So this is called an adversarial example, which is ubiquitous in vision, computer vision. And in this picture, actually, I guess many of you saw that that's the Sora created by a modern diffusion model using Sora to create some video. And I think I don't have time to show, but if you search on the YouTube, Sora video generation, woman walking, then you can find the original video. So although the original video is very impressive, looks very realistic to human eyes, but if you look at, you measure the detail of this, the images in this video, you find the projective geometry fails to be preserved. There's no focus, although it looks very realistic. And this kind of thing, actually, the second example is showing that AI can cheat our eyes, not like a human. So this shows the difference between AI and human perception. So This is the other example. People use ChatGPT a lot. You can easily find the facts are lost in the generative language models. So in those examples, actually, we can see the current deep neural network, although very powerful, learned from the big data, but they lack the stability of physical environments. So that's the crucial difference between the current development of AI models and the human ability. I don't know what's the future limitation or what's the future development, whether we can fill in all these things. But the current society, people try to add more data or constraint like a chain of thought to align those machine learning models toward trustworthy ones. So there are a lot of effort along this line. And why this happened? Maybe I just show a couple slides saying that because this is the difference between the human and the current, say, convolution neural network, they rely on different features. So Misha Bell can talk about the importance of features, but what kind of feature essentially used in those neural network. The one example is in this. So people actually argued for every dense trained dense network, there exists a subnet which has the same efficiency, saying the same performance in the prediction power compared with the dense one. And this Franco and Carbon 2019 paper actually gave you a simple algorithm. You can train the subnet from the same random initialization of the dense one, and then you can find this efficient subnet. But if we apply this kind of technique to the ImageNet training network, and we always use early stopping to find them in early epochs, then we try to visualize those intermediate layer features. This is supposed image like a snake. We can try to see what kind of feature we use to classify this snake properly. Then those images represent on the left top will be the most important feature. On the bottom right will be less important feature. So this is the stochastic gradient descent. These are our algorithm designed specifically for this kind of thing. But you can see the surprising way, for ImageNet trained neural network, they does not rely on the shapes or color. It's different to human eyes. They rely on some non-semantic features, which are texture, we call texture bias in literature. So that's characterize the significant difference, crucial difference between the human perception and the current neural network perception trained using ImageNet. I don't want to go too much in detail, but this is actually come back to the thesis work with Steve Smale, where I start this kind of pursuit. So when I arrived at Berkeley, and Steve just finished this paper with Cooker Smale on mathematical foundation of learning, and Paul already showed that. And at that moment, we want to do something more. This is a laid down mathematical foundation for learning, and what else we can pursue in my PhD. And to think about this question, Steve just met this John Tsitsiklis, professor in MIT, in a flight. They go to the same conference in the same city, and when they come back, they share the flights. And then John Tsitsiklis says, he's a big expert on reinforcement learning. He said, in reinforcement learning, people essentially use online samples, sequentials, but compared to the mathematical foundation of learning at that moment, they lack a solid foundation. Even how to learn a simple function using ID samples in online in a sequential way, there is a lack of theoretical foundation. Then they propose Steve Smale. Maybe you can ask your student to pursue this direction. And then Steve immediately in the flight write down some formula in the paper, and then come back to show if you can show upper bound exists for this formula, which is basically calculus, then we can pursue to this online learning scheme. They believe that kind of formula lies in the hardcore of the online learning algorithm analysis. Then after a couple of days, then we figure out, both figure out how to get the upper bound, then we pursue this journey. So that eventually becomes this FOCM paper in 2006. I think the original motivation, we should give credit to John Stiklis. And even his original proposal for online reinforcement learning has never been established like what he expected at that moment. Even nowadays, I think next spring in this institute, there is a program. One of the workshops is about online reinforcement learning. So online reinforcement learning currently only focus on the finite state and finite action. So it's a very lag behind the learning theory. But anyway, that's the thing. And starting from this paper, we established some solid theory. And at that moment, Pierre Therese, he also joined Chicago in a workshop organized by Steve Smale and Pasan Yelgi. Then we worked together. After many years later, we are a little bit lazy. We set up the first kind of bond, but eventually finished correction and revision in the year 2014 when Pierre joined Oxford University as a faculty. Then we established the optimality of this kind of algorithm analysis. And then simultaneously with Lorenzo Rosasco and Andrea Caponetto, they also joined Chicago. Then we also work on another paper, which becomes very popular recently about early stopping regularization. So that's a kind of, I would like to view that's a kind of exercise to extend from the classical approximation theory to the random design learning theory. But after that, I keep in mind to pursue the algorithm from Euclidean algorithm, the gradient descent in Euclidean space or reproducing kernel Hilbert space to some non-Euclidean gradient descent. Later, I met Stan Osher from UCLA. They use Bragman iteration that can be regarded as a very special case for the mirror descent, but a very powerful algorithm, a very efficient algorithm in compressed sensing. Then we establish a new analysis for early stopping and model selection consistency. So that one actually was used to generate this kind of how to learn what kind of feature we learned in the neural network. So that's later. Okay, so this slide I can skip. That's about what's the mirror descent. But another thing is we also explore non-gradient based algorithm, because gradient-based algorithm for multi-layer network often suffer the gradient vanishing issue. But we can find some classical algorithm from optimization, or especially decentralized distributed optimization like ADMM and block quantum descent, and that can be used to alleviate gradient vanishing. That's a kind of strange because people can write gradient descent as a Lagrangian multiplier method. Yan LeCun has a paper in 1988 to do that exercise. But very few people really use this Lagrangian multiplier idea to pursue other type of algorithm like ADMM and BCD. I think this can be exactly useful maybe for Tommaso's compositional sparsity. If we know the intermediate step, then we can do optimization more efficiently. So the result is actually, if this algorithm essentially explore this idea like BCD, if we know the intermediate step, even approximately with certain error, then the multi-layer network training can avoid the gradient vanishing. So this picture simply says in stochastic gradient descent, if you train to the early layer, they never change. If you have too many layers, this may be 7 or 8. But in ADMM type, they are very sensitive to the output. So this is the kind of idea. That's also work with Dingxuan Zhou. That's Felipe's colleague in CTU, but now in Sydney University. Okay, so I think maybe I don't have too much time. I just want to say another line of research on topological learning from data. And Steve not only established the previous one, noise-free version, but also he has the noisy version in 2011. And this published after PASA passed, actually. And then people also developed lower bounds, and TDA, actually, topological data analysis evolves in different categories. Persistent homology are mostly pursued by the computer scientists and Gunnar Carson's group in Stanford. And that can be comparable to Forman's discrete Morse theory. So this is also one connection to Morse theory, the Steve Smale early work, but this is in the discrete sense for one-dimensional persistent homology. But on the other hand, the Hodge theory, which is a bridge between geometry and the topology using the analysis and optimization, that can be also important. In fact, people pursue this direction a lot further, like 2022, Seth Lloyd in MIT group using the linear algebra quantum speed up to show TDA actually you can speed up quadratically. And this is a Nature Communication paper. And Steve Smale write a solid paper about how to use the Hodge theory to analyze the matrix-based homology. This is the 2012 paper. And we particularly apply Hodge theory in the combinatorial setting in the preference learning, how to solve the social choice. And that's our pursuit. I think maybe I can stop here. And the later things I can jump that.
Okay, thank you.
Okay.
Yuan, or you want to start?
Yeah.
Questions?
Yes?
You mentioned a result that given a big network,
Yeah.
neural network, there exists a subnetwork which is almost as efficient.
Yeah, this is only empirical observed by Franco and his maybe student and in the MIT group. Yeah, 2019, that becomes the best paper in ICLR. They do lots of experiment in computer vision, train a dense network. Then if you prune the dense network after training, and you pick up a subnet, maybe only 20% of the sparsity of the original one, then you retrain this subnet using the same random initialization of the dense, then they can reach a network in a similar step of training, that reach a network with similar performance of the dense one.
Nice result, but my next question is that was just an introduction.
Yeah.
Now, is there a method, even empirical one, to contract the big network, to extract the optimal subnetwork?
Whether it's optimal, we are not sure. It's only give one way. Yeah.
Okay, but better, smaller and as efficient.
Yeah.
A method of discovering it?
Yeah, we actually can use the non-Euclidean gradient descent or mirror descent. We can let the network parameter only evolve and the gradient descent only evolve in the subspace of important parameters.
I see.
Yeah, that can give efficient subnet in early epochs rather than fully train network to a dense one, then prune that with a small, drop the small weights, then retrain from the initialization. We can just follow the early epochs and get a structure.
Nice, thanks. I approach you later for the reference because it's very interesting. Thank you.
Okay, thank you.
Okay, so we have so we have a break again, and followed by two other presentations and a round table discussion. Right, thank you.
people.